Welcome back to part 2 in our series of videos on life cycle assessments. Our previous video was the first in this new chapter of the series. If you recall, we took a deep dive into the goal and scope definition phase. Now this time around we're going to do the same thing with the LCI phase. We're going to take a look at just what we need to do to make this phase work, and we will consider our two favorite ISO standards, ISO 14040 and 14044. We've got a lot to discuss, so without further ado, welcome to the LCA study and the LCI phase. This is your guide to the life cycle inventory analysis. Starting with a quick overview. The LCI phase consists mainly of building an inventory of inputs and outputs with respect to the system under analysis. Collection of data is undertaken to meet the goals of the study. In fact, the definition of our goal and scope provides an initial plan for conducting the LCI phase of the lifecycle assessment. We sort of talked about this a bit in the previous video. We also talked about how, for your study of your product system, this phase may be the main or indeed the only executive phase you decide to include. Remember that if you omit the LCIA, the impact assessment phase, you are in fact conducting an LCI study rather than an LCA study, and your format and content of your report should reflect this. You can find more details in the terms and definitions video or in the dedicated LCI phase video coming soon. But the point I want to focus on first is the data collection. And before we do that, first of all, remember that inventory analysis is iterative, like most of the rest of this LCA, as well as this disclaimer itself. It's iterative. It might keep happening. This means, of course, that you might need to revise your data collection procedures as time goes on, and maybe even go as far back as your goal and your scope. With that being said, let's start with a simplified procedural block diagram of an inventory analysis, so that we can have some visual context. Keep in mind that I'm not showing any of the iterative steps here, just to keep things as straightforward as possible. So, after we've defined our goal and our scope, we move to the data collection, where we prepare for collecting data with a respective data collection sheet, and then collect and validate the data afterwards. This means making sure that it's comprehensive, complete, and representative of the goal and scope. The validated data then gets passed to the data handling portion of the LCI phase. This is where we spend some time relating our data results to the unit process, as well as the functional unit of the system. This process creates a representation of data as a relative flow, and we can use that model to perform aggregation on the data later if necessary. So, at the heart of it, it's a pretty straightforward process, although keep in mind we are omitting the iterative elements from this procedure. We may have to rethink our data collection sheets, for example. We may need to start again if we can't validate the data we have collected, or if we need to redefine our system boundary or even our allocation steps. This diagram is a simplified linear representation of the process, and it's important to remember that we're always checking our progress. We're always verifying our data and confirming that our methodology is correct and in line with the principles and guidelines of the study as outlined in ISO 14040. I hope this provides some context for the framework upon which we build our LCI phase. Now we can truly move on and discuss the data collection portion of this phase. We start by identifying our unit processes that make up our system within the system boundary. Our goal is to collect both qualitative and quantitative data for each of the unit processes. The data we choose to collect gets included in the inventory, and regardless of source, they are used to quantify the inputs and outputs of their associated unit process. We need to exercise caution at this point. We don't want any misunderstandings about our product system to creep in at this stage of the study. This can come about by, for example, double counting an input, or accidentally reusing a stock or flow when you're doing allocations or splitting them up into different flows. To avoid this situation, a description of each unit process should be recorded alongside the data being collected within it. This can help later if we find that we do indeed need to audit our inventory in some way. When we start collecting data, we want to classify it for each unit process under some important categories. These include the following: inputs, which are things like energy, raw materials, ancillary inputs, and any other physical inputs. Products, which also includes things like co-products, byproducts, and any waste or scrap materials. Environmental releases, which include any emissions to air, discharges to water or soil, or other environmental considerations that may be pertinent to your study. Our ultimate strategy is to detail these individual data within these headings, whether by subcategorizing them or some other method. We do this in order to satisfy the stated goals of the study. Now, it may be the case that you're a small enterprise with a single location and just a few products, and so you might be able to collect your data from a centralized point with relative ease. But this isn't the case for everyone. Data can come from many sources, and it's important to know how to handle whatever you come across. For example, if you use publicly available data, it should be referenced in a standardized way. If this data is significant to the conclusion of the study, then it should include further details such as the collection process, the time when such data were collected, and detailed information about the data quality indicators. In fact, in most cases, data collection can span several reporting locations and sometimes hundreds of published references. This is why measures should be taken to reach a uniform and consistent understanding of the product systems you're attempting to model. Keeps things a lot easier farther down the road. These measures should include the following at minimum: describing the data collection and calculation techniques needed for all of your data, describing each unit process in detail with respect to factors influencing their inputs and outputs, listing flows and relevant data for operating conditions associated with each unit process, drawing unspecific process flow diagrams that outline all of the unit processes to be modeled, including their interrelationships, developing a list or legend that specifies the units that will be used across the study, and finally providing instructions to document clearly any special cases, irregularities, or other items associated with provided data that you think needs special attention. Data collection can be an extremely resource-intensive process. Remember that we spent some time last video talking about the importance of a well-tailored scope. This is where you can justify any practical constraints that you're considering in your study, which will affect exactly which data you seek to collect. Always remember to document any such constraints in the study report, of course. Finally, you may feel a bit overwhelmed at this point when you go to actually decide which data you will collect. The LCI phase is the first executive phase of the LCA, and the bandwidth of activity needed to complete it is considerably broader than our last phase, the goal and scope definition phase. That you will see. So it's useful to know that Annex A of ISO 14044 contains examples of data collection sheets that you can use for inspiration if you're having any difficulty starting your own data collection procedures. So once you've finished collecting your data, you can begin the various data calculation steps. These are intended to transform your raw data into a format that can be passed forward into the next phases of the LCA. If we take a more formal definition from the standards, calculation procedures generate the results of the inventory. Your inventory belongs to the functional unit you've defined and the product system you've modeled, and it's important to reiterate that the inventory also spans each of your unit processes. Now, the term calculation procedures encompasses several different possible operations. It can include things like data validation, relating data to unit processes, and relating data to the reference flow of the functional unit. Whatever procedures you do employ, they should be explicitly documented, alongside any assumptions you've made, which should themselves be stated clearly and explained thoroughly. Also, Your calculation procedures should be applied consistently throughout the entire study. Don't go changing things up once you hit the impact phase, for example. So before we explore these calculation procedures further, let's talk about another couple of special considerations that you may face when you're developing your inventory and how you might be able to handle them. First of all, let's talk about energy flows. Energy flows can be tricky to account for. Calculations associated with energy flows should account for three main considerations. First, all of the different fuel and energy sources used. Second, the efficiency of conversion and distribution of those energy flows. And finally, all of the inputs associated with generation of those flows or their use. In the last video, we used an example of a restaurant trying to lower its usage of natural gas. This is an example of combustible material used for energy flows, and these also have a special consideration. Namely, inputs and outputs related to combustible material can be transformed into the respective energy flows by multiplying by that material's heat of combustion. This can usually be found in the materials material data sheet or in various standards guides, for example. You should also report whether or not you're using the so-called higher heating value or lower heating value when doing these calculations. Secondly, elementary flows. Remember, these are flows between the product system and the environment that don't involve any significant human interaction past the act of gathering. When determining your elementary flows associated with production, the actual production mix should be used to reflect the various resources consumed when possible. As best as you can, try to establish a ratio of inputs and use that set of weighting parameters to model the flows properly. So now that we've looked at what it means to calculate your data, let's look at how we can actually go about performing these calculations. ISO provides operational steps that you should follow when doing your data calculations. You can either perform them in order or else in tandem, whatever works best for quantifying your product system. Let's look at these operational steps in some detail. Our first step is data validation, and I know I said you could do these steps in any order, but you may want to start with this one. Remember back to when we were defining our scope. Constructing our scope rather, we defined some initial data quality requirements. When we perform data validation, we check our collected data against these quality requirements and verify that they have been fulfilled. This is done by creating some sort of validity check. Your check could be a listed standard for the purity of some metal that you're working with. Or maybe you've got some recent calibration results from the machines that you use to make your product, and you can use those to verify your results. You can even take advantage of natural laws, like the conservation laws of mass and energy. Whatever you've got, whatever makes the most sense to confirm your results, that's what you want to use. You then conduct that validity check and generate evidence that your initial data quality requirements have been fulfilled. Now, of course, I say initial because once again, the LCA is iterative, and we might need to redefine them later on. But you'll know whether you're on the right track once you perform this validation step and get a sense for the quality of your data and the effectiveness of your collection methods. The second operational step for performing your data calculation is the process of relating your data to the unit process and functional unit. That's sort of a nebulous requirement, so let's break it down a bit. First, look at each of your unit processes. Once you've got them organized, determine an appropriate flow for each one that is based on the data you've collected. Once you begin your calculation steps, the quantitative input and output data of those unit processes are calculated in relation to those flows. Then, once you've dealt with each unit process in this way, zoom out. You now want to relate these flows connected to the unit processes to the reference flow of your functional unit. You do this based on the chain of flows through your product system, paying extra attention to the flows related to the unit processes. In this way, you'll start to apportion parts of your reference flow to each of the unit processes, which will in turn provide the details relating to the distribution of those resources over the different parts of your product system. It probably sounds like a bit of a tedious process, and it can be, and you might be tempted to aggregate some of your data at this point to make it easier. That is allowed, just be aware that data aggregation at the product system level comes with certain restrictions. It may in fact be more appropriate to list your flows in full at this stage without the aggregation and perform that aggregation later on in the study at a later phase. Another important operational step in calculating data is incorporating the refinement of your system boundary. This is something that you'll notice comes up a lot. We talked about it even in the video on the LCA goal and scope definition phase. And we sort of expect this, right? LCA is an iterative process, after all. There's that word again. So this step concerns decisions you make regarding data to be included in the study. These decisions should be based on a sensitivity analysis that you develop for this purpose so that you can determine the significance of the data. And in this way, further verifying the initial analysis outlined in the scope. Indeed, your initial system boundary should be revised as appropriate in accordance with the boundary cutoff criteria that you established back in the scope. As well, keep in mind that your sensitivity analysis might also have some unintended consequences. For example, you might find that some life cycle stages or unit processes that you intended to include in the study just aren't very significant after all. Or on the flip side, some parameters you thought were insignificant and you could just ignore them, they may play a bigger role than you had realized. The results of the sensitivity analysis may suggest that you therefore add or remove these stages or processes. The same can be said for inputs and outputs that don't end up having much significance to the results of the study. Remember last video, we talked about, for example, a primary industrial process that creates 10 times more volume of some pollutant than its auxiliary processes, and therefore we decided to exclude the auxiliary processes from the study. Your sensitivity analysis might actually be the tool that helps you recognize that fact and come to that decision in the first place. Something to keep in mind. Now notice that this sort of self-checking mirrors what we did when we defined our scope. These additions or subtractions by way of the sensitivity analysis can help reduce the load of subsequent data handling for those inputs and outputs that are truly significant to the LCA goals. Later on in the study, I mean, it can reduce that data handling later on in the study if you address it at this stage. And once again, it goes without saying, but I'll say it anyways, your sensitivity analysis should be thoroughly documented. This includes the refining process that we just discussed, and any results, assumptions, or justifications that you use. Alright, let's talk about one more operational step, the allocation of flows and releases. This is a particularly important step, so let's take a moment and recall the definition of allocation, as provided by ISO in the standard documents. Allocation is the act of partitioning your flows between your system under study and other systems. Let's take a moment to recognize that most industrial processes usually yield more than a single output, or else they have a linear relationship between their inputs and their outputs. This is a simple but effective assumption or model, however you'd like to call it, to adopt to start performing that allocation, because it allows for intermediate and waste streams to be accounted for, and that's definitely something we're going to want. Allocation procedures for these byproducts should be considered whenever you're dealing with multiple products or if you're going to have to account for recycling. We'll address that last point in just a second. First things first though, let's dive right in and look at the allocation process from a high-level viewpoint. A couple of videos ago we learned the golden rule of allocation. The sum of your inputs and outputs before allocation should equal your inputs and outputs after allocation. Think of it sort of like the laws of conservation of mass or energy. When it comes to anything crossing the system boundary, regardless of how we partition it out, we must ensure that we aren't creating anything out of thin air or destroying things that need to be recognized as we move deeper into the study. When we allocate our inputs and outputs, we allocate them to different products according to specific procedures. Defining these procedures is part of the allocation process, and the definition should be recorded right alongside the rest of the allocation documentation. Remember when we looked at an example of making hammers? The raw lumber gets allocated to the hammer handles via the procedure of crafting those handles. We expect other inputs to be required for this procedure, and we would need to allocate them as well, of course. Once the procedure is done, we then allocate the handles to the finished product via the procedure of assembly, final product assembly, whatever you'd like to call it. Once again, we expect other required inputs like the hammer head, maybe some adhesive or something else, and all that would need to be allocated to in that other process, in that other procedure. We might expect some additional outputs too, right? Waste and scrap and some kinds of pollution. Depending on where all of those things end up, we might need to allocate for those output flows as well, again, by defining the specific procedures through which they are generated or utilized. One final point to conclude this overview. If we're ever in the position that several different allocation procedures seem like they could be applicable to our situation, we should simply select the one we like the best. Nice and easy. However, we would also be very well off, and this is my point, to conduct another sensitivity analysis at this point, and explore the consequences of what would happen if we did depart from the selected approach and tried something else instead. The results of that should be included alongside the decision you've made. So now that we've got a general idea of what allocation looks like, let's talk about how we actually perform it. Let's summarize our progress so far. We've defined some goals for the study and started to fit our focus into a scope of operation. We've identified a functional unit and reference flow that are representative of our product system's performance characteristics. We then defined a system boundary, and within that boundary we identified our unit processes. This is how we've modeled the workings of our product system to this point. Then we collected our data, performed some calculations, verified it, and now we're ready to push that data forward. How do we do that? Let's go to the standards and see what they say. I'll paraphrase a quote here. The study shall identify the processes shared with other product systems and determine allocation status according to a stepwise procedure. So that means collect your data, do the calculations, and then follow the steps. So let's follow those steps now and see what it recommends. Step 1 is preemptively trying to avoid allocation wherever possible in the first place. Allocation is a messy process, as you might have come to understand, and we've still got a bit to talk about it just in this video. That means it's in our interest to simplify our study, if possible, by sidestepping allocation altogether. There are two ways you can do this. First, by re-evaluating your unit processes. Try to see if there's any processes that you can divide into 2 or more sub-processes, and then redefine the associated input and output data to relate to those sub-processes. Think of it like a computer programmer that has a single large block of code, and they want to streamline it by dividing it into distinct class and object files. The resultant functionality is still the same, but the information passing between the components becomes somewhat compartmentalized and standardized in that way. A second way to avoid allocation is by expanding the product system to include the additional functions related to the co-products in question. This will mean taking into account the system boundary requirements as laid out in the scope definition phase, and ensuring that you account for any externalities that come with that increase in scope. Now sometimes it's worth it, and you end up, bringing flows back into the product system, and therefore you don't have to allocate them. Sometimes it might just make things harder though, since the new functions you want to include might come with their own baggage in the form of additional product or elementary flows. So use your judgment if this is indeed the avenue you select out of the two. Now, if you just can't avoid allocation, you tried the 2 previous suggestions and they just don't work, we move on to step 2, which is allocation based on physical relationships. What this means is that the system inputs and outputs should be split up between your different products or functions, such that we represent the underlying physical relationships between them. That is, allocation should reflect the way the inputs and outputs are changed by quantitative changes in the products or functions delivered by the system. Let's bring it back to an example. Let's talk about the hammers again. We first feed lumber into the process that creates the hammer handle. If that's the extent of the product system under study, we could then allocate the hammer handles to the process that assembles the hammer to create the finished product. This allocation makes sense because of the nature of the handle. It is crafted specifically to fit the hammerhead that we are also making and create the final hammer. In this way, we justify the allocation based on the physical relationship that exists between the products of the two systems. Now, your network of product systems might be much more complicated than this, but the interrelations built between them can be constructed using this method, and in this way we allocate our inputs and outputs such that everything eventually gets accounted for and nothing gets lost. You may also find that there is no physical relationship between the products, or that a physical relationship alone isn't enough of a justification to use allocation to relate them. If this is the case, we move to step 3 of the allocation procedure and focus on other relationships that might exist between them. Let's consider an example. Think of a foundry that purchases various raw metal ore from suppliers and produces purified metals. Now, some of this ore might contain only common metals like iron or aluminum, and some of it might contain rare or precious metals like gold. Now, for simplicity's sake, let's make a few assumptions. Let's assume that we need exactly the same amount of time and heat and energy to extract the metal regardless of the ore. Let's assume that all of the different ores use exactly the same, say, chemical additives, fluxes in this, to assist in the extraction. And let's assume that all of the ore that we receive contains the same density of metal. Now, these are all big and kind of arbitrary assumptions, I know that. But what this allows us to do is say, okay, now regardless of what we process, the only real difference in our production is how much we can then turn around and sell the resultant metal for afterwards. Now obviously gold will sell more than for iron and aluminum, so all things being equal, it's more profitable to process gold than iron in our foundry. Since the input costs are the same and all of the co-inputs are the same, therefore the only difference is how much we can sell it on for. This should be pretty self-evident. So what's the point of this example? If we need to allocate the co-inputs in a system like that, the fuel, the flux, whatever, we could make the argument that we are allocating them to the various metal product systems based in proportion to the economic values of the respective products. This allows us to distribute the coal or the coke or the lime or the flux weighted with respect to the value of the different products and avoid the need to put all that effort into defining a strict physical relationship between them. Now, you might find that some of your outputs are partly co-products or partly waste. The metals industry is a great example of this, in fact. In this case, it is especially necessary to identify your exact ratios, since your inputs and outputs are allocated only to the co-product part and not to the waste part. And that's the stepwise procedure for applying allocation to your product system. I know it was a bit long-winded, but keep in mind there's only 3 steps. And one of them is trying to avoid allocation altogether. So in your own study, here's a few final tips to help you with your own study. It's actually just one tip stated in a lot of words. Firstly, the allocation procedures applied to similar inputs and outputs should be uniform within your system. What does that mean? So for example, let's say you make smartphones, and part of your production line involves manufacturing the hundreds of different little parts that you find in a modern device. You might find yourself, for example, discarding imperfect parts, right? Or else saving stocks of intermediate parts to sell on to, say, third-party repair service providers. You might also have a recycling scheme in place, and that lets you collect broken phones and recover parts that you can put back into the production line. With this set of circumstances, the allocation procedures that you use for the co-products coming into the system should be similar to those used when they exit the system. This tactic helps with keeping the flows uniform between and within the systems, and it also assists in tracking volumes between the systems to ensure nothing's getting lost. So between this video and previous videos, we should now have a pretty good understanding of how to apply allocation to our product system. We do need to talk about one more special set of circumstances that might require allocation, and that is what happens in the cases of reuse or recycling. I told you we'd get back to it. This is a special case because of the nature of the inputs and outputs. In this case, they are no longer strictly inputs or strictly outputs. You see, I kind of tiptoed around this point when I brought up the previous example of being a smartphone manufacturer. I hope you can see now that that example is actually flawed. I used it to illustrate my point, and I hope it worked in that way, and I'm sorry to pull the old high school trick of everything I've just told you is a lie. But the truth is, when you're allocating these types of flows, we need to take a few more things into account to be complete and precise. The first thing to say is that the general allocation principles and procedures that we just spent some minutes talking about, they also apply to reuse and recycling situations. We add the first bit of extra detail by tracking changes in the inherent properties of the materials in question. That's what differs from the procedures we just talked about. So do they change quality? Do they change state? Things like this. This requires a very explicit delineation of the system boundary for the product system in question in relation to other systems. And this is especially true for recovery operations over recycling operations. It's necessary for both, but it's especially true for recovery. Secondly, we need to provide additional elaboration about our recycling allocation procedures. This extra detail is needed for a couple of reasons, but our main consideration is the change of inherent properties of the materials, like we just discussed. And because the flows associated with reuse and recycling can be very complicated. For example, looking at a graphic like this that represents a sample product system might imply that the inputs and outputs associated with our unit processes are shared between more than one system. This is relevant for extraction and processing of raw materials, for example, and final disposal of your products. It's another situation where a little extra care in setting up your system boundary can largely account for this consideration and save you a whole bunch of effort at this stage if you're just doing it piecewise. And again, LCA is iterative, so if you do reach that point, and if you do need to do so, back up now. Go and redefine your system boundary and progress through the study again to see where you end up when you've returned to this LCI phase stage of allocation procedures. Thirdly, we need to ask ourselves whether our product system is a closed loop or open loop model. This will determine what sort of allocation procedure that you will apply to the system, which affects how you will proportion, say, virgin materials and recycled materials across your product system. Open loop and closed loop systems are a bit outside the scope of this video, and we are running on here, so I will point you to the ISO standards because they provide a good primer, and there are plenty of free resources out there as well to understand the definition of these systems, how they differ and what their applications are. These can all help you determine if your product system is open or closed loop if you don't know already, and therefore any special considerations that you should apply to your allocation procedures as a result. A final note on allocation procedures for recycled materials. We talked about a stepwise operation for applying allocation. First we see if we can avoid allocation altogether, right? But since we're talking about the allocation of recycled materials, we're going to skip that one in this instance. Next we see if we can link products based on their physical properties like mass or energy. This still holds true. Next, in the stepwise operation, if that doesn't work, we look to other links, other interrelationships that we can use as justification, like economic value. This also still holds true. When we're talking about recycled materials, however, we add one final step to the operation, and that is the consideration of the number of subsequent uses of the recycled material. That is, virgin material versus recycled secondary materials versus heavily recycled secondary materials, things like that. The exact way to apply this final step depends on our previous point, which is whether your product system can be classified as open loop or closed loop. If this does indeed apply to you, take a moment to check out the standard at this point and understand exactly how you should apportion the different grades of your input and output materials with respect to your personal set of circumstances. So that's the video for the life cycle inventory analysis phase. I hope you found it useful. In the next video, we'll move on to our next executive phase of the life cycle assessment, which is the life cycle impact assessment phase, where we take all of the data we've crafted in the LCI and use it alongside various environmental considerations. It's a very important phase, so be sure to stick around and check it out. I'm Jamie Freno-Cumbo with EnviroPass. Thanks for watching.